So how does this work? So each parameter is going to be updated with a new value derived from its old value plus taking a step in the direction of the gradient. Okay, and so in these plots, remember this is the coordinate pair theta 0, theta 1, right? That's the space we're in. And at iteration 1, the point is here, and at iteration 2, the point is here, and iteration 3, and so on. Okay. So in order to get iteration I plus 1, we're going to take the same value, the value of the parameter iteration I, and add this offset term. Okay, so what's going on with this offset term? So this is the learning rate, which is just the step size. How far are we going to go in that direction? Okay, and this is usually a small value, maybe 0.001 or something. Okay, but it's application specific. It's a bit silly to even state what it should be. However, I didn't notice that in this example I did scale everything down to a value. So 0.001 on scaled data may not be an unreasonable thing to use as a default. And so this operator is the partial derivative with respect to theta 1. And if you remember, a little bit of college calculus, the sum of these partial derivatives is the gradient. And so we're just doing one of these, partial derivative with respect to one particular variable. Okay, and then j is our cost function that I haven't shown yet. And j will be a function of these parameters as well as a function of our data set. Right? We're going to take these parameters plus all the data set and compute some new cost. So blowing up j, so this is our model at iteration I. Right? Remember, we're trying to compute the new value of the parameter at I plus 1. Apply that model to the data instance x, subtract the the true value, the correct value y, and that's our error, square that, and then add it all up for all possible values in the data set, which is what k is, right? So we're going to run over all of our data points, check the difference, square it, add it all up, that'll be the value. And actually divide by 2 here, but that's more just to make things work out. So you'll see that a lot. It's divided by a constant factor, so it doesn't actually change the direction at all. Okay, and so now we just need to differentiate this with respect to the parameter that we're updating, in this case theta 0. Okay, so this is elementary college calculus, but just to show the steps on one slide, push the partial derivative through the sum and then apply the chain rule to get this 2 factors. And then remember that h, our model, is actually just a linear model, so we're multiplying the x value times the slope parameter, adding in the y-intercept. And the only term in here that involves theta 1 is this theta 1 times xk. So the other ones don't involve theta 1 at all, so we can just drop them. Their derivative is 0. And so this just simplifies to xk itself. And so h of xk minus yk times xk is the update rule that we're looking at. So this is just sort of putting the starting point and the final point together on one slide. So the overall update rule looks like theta at I plus 1 equals theta at I plus the learning rate times the sum of the value that we predict for xk minus the true value times xk. And so overall what you say here is, while not converged, apply these update rules. Update theta 0 and then update theta 1. Okay, and then check for convergence. And so that's the program that you could write if you were going to implement this by hand. So one detail here, why is theta 0, for the theta 0, why don't we have this multiplied by xk? Well, the reason is that because it's the y-intercept, there's not an x value to multiply by, so it's actually just assumed to be 1.0. And in fact, you can think of this as adding an extra. If you've got a single attribute, right, our x values, and we're trying to predict y from x, we can think of it there actually being 2 attributes. One, our x values, and the other one being a constant attribute, where every single instance in our data is just the value 1.0. So it has no effect on the learning, but it allows us to have, an x variable for every parameter. So there's sort of a trivial x0 right here, and you can assume that x0 is always 1. Okay. In which case, then it would also appear out here. So some questions that arise from here, there are still some parameters to this process that have kind of leaked in, right? There's this initialization step of where we decide to start the process, and we have to choose that point by some mechanism. Okay, so you might have sort of small random values, or you might pick always the same point, and random, as usual, gives you a little bit of robustness. Okay, and then you also need to decide the step size, and this procedure is, notoriously sensitive to choosing a step size. So if it's, we don't really roll, we're not doing a kind of a continuous fall down the gradient, we actually have to jump, and so we have to figure out how far to jump. So if you jump too far, you might actually skip over the minimum and come up with a higher function value rather than a lower one. And so some of the methods to decide this learning rate will adapt based on how much of a difference in the error rate you've gotten. So if you're rolling on a relatively flat period, you might take a bigger jump, while if you're going through a regular steep period, you might take a smaller step. Okay, in order to sort of keep approximately constant the amount of gain you get in the error. And so that's one trick you can do to sort of avoid this decision about the step size. Otherwise, people sort of tune it in an application-specific way. Okay, and if it's too small, then you'll sort of fall within the gradient, but you'll take a very long time to get there, and you have to also doctor in the convergence test as well. Whether it's above the threshold. Okay.